UCLA talk on formulations of community detection in terms of total variation and the surface tension. Surface tension might be second order thing or not.
Thank you. Turn this on. Okay, so this is a little different from the other talks that have been given here so far, as it's not explicitly about images, but I will mention applications to images in here. This is joint work with Andrea Bertozzi, Shicheng Tai, Egil Bai, and Mason Porter, mostly based on two papers, one of which is not quite on the archive yet, but the results are essentially finalized at this point. And the basic idea of this talk is that there is a bridge between work that's been done in the variational methods for imaging and materials science and the newer network science models for community detection. So I'm going to describe the intuition and some hard results about that bridge, and a couple of applications, and hopefully this will spark further work, because after working with this for a while, I'm convinced that there's enough of a connection here that technologies can be ported back and forth between these two domains, and so there's probably some opportunities to leverage work in the different fields. So I'll spend a fair amount of time introducing everyone to some aspects of the network science and community detection problem, and then after that I'll describe basically two big theoretical connections and the applications of them. We'll go that far. Okay, so in image processing, I'm aware of three kind of main ways that you can get graphs or networks. There are probably others, but in one case there's the spatial graphs, where you just take an image as a collection of pixels and make each pixel a node and connect those nodes to the adjacent nodes. So you'll form something like a four-regulared grid. Although there are various elaborations on that, and this is used in the graph cuts literature for image segmentation. Another way that you can get graphs is essentially using similarity graphs via the non-local means trick and other things. So the way this works is that pixels are still the nodes, but you don't connect them to their spatial neighbors. You connect them to other pixels that have the most similar neighborhoods to them. So for instance, in the baboon picture down there, both sides of the baboon's nose are the same color, so they would be more likely to be connected in the non-local means graph, even though they're not spatially connected to each other. And then a third way that I've seen this done in the imaging literature is via networks of images. So the simplest example is MNIST, where you have all these images. You can maybe map them to some feature space if you want to, and then just make a similarity network in that feature space where each picture is linked to its nearest neighbors in that space to form a graph. You can pick a cutoff, say the top 10 nearest neighbors or something like that, and then do graph clustering to try and understand, or to try and basically do unsupervised learning about the structure of the data set. But the graphical methods are used far beyond the image sciences. I think most of us are aware that social networks are becoming an important object of study, such as Facebook. But there are many other kinds of networks, transportation networks, brain networks. Notably, there's a huge literature developing on people trying to understand the linkages of activity within the brain and other parts of the body, and trying to uncover the latent structure in those interactions. And network science is one of the tools they use for that. I think the food web is another notable one that people don't usually think of. This is where in an ecosystem there exist many different species, which will be related to each other in different ways. For instance, one will eat the other, and this forms a really important network of interaction that's the subject of a lot of study, especially by people who want to maintain the stability of the food web. And so they'll do studies of the nature where you'll say, okay, if there are 10 nodes in this network threatened and we can only save 3 of them, which one should we save? How will our different choices affect the stability of the network dynamics? Yeah, and so anyway, there's all kinds of things that people in other fields are trying to do with these graphical models. They'll usually call them networks instead of graphical models, but there's a lot in common between them. Another example that I think is worth mentioning is the protection of networks. I talked about that just now in the context of food networks, but there's also the application to technological networks where it's thought that malicious actors might be trying to bring certain nodes or edges down, and people want to know what the effect on the network would be if they succeeded, and are interested in optimal network design in terms of robustness to various kinds of attacks. So people in all kinds of fields are studying these graphical models and calling it network science. One thing that's kind of emerged as true across a lot of applications is that the graphical, or the graphs and networks that arise from this kind of analysis are usually modular, in the sense that the connections are not regular, in the sense that there's not usually much of a symmetry group on the network, but there is some kind of coarse-grained structure. And so the image that's shown there is just a synthetic network, but it's designed to have the properties of networks from many domains. And you can see there's kind of a clumping together that occurs. And inspired by the social network setting, this is usually referred to as community structure. And it's one of the biggest problems in network science, basically because most networks that we come across don't have the kind of regularity that we're used to in Euclidean space and in manifold theory. And so the nearest thing we have to be able to summarize and reduce the data is basically this community structure. There are other tools as well, but this is one important one. It turns out, though, that even though everyone basically agrees that extracting community and modular structure from networks is really important, the problem is extremely difficult to define in a practically useful and computationally tractable way. So at first people thought that this would turn out to be relatively simple. They'd say a set of nodes is a community if it has more inlinks than outlinks, right? The nodes link to each other more than they link to others. It turns out that a definition like that allows you to find community structure, strong community structure in things like Erdős-Rényi random graphs, where it's known that there's no mechanism that's causing the structure. And so people have moved, the biggest movement has been in a statistical direction, where instead of observing fluctuations in the number of nodes, people are trying to understand the significance of fluctuations in the formation of edges. So, for instance, one of the most common ways is to pose a generative model for the network that, there are these latent variables that are the community identities of each of the nodes, and this somehow influences the edge formation. And once you have a probabilistic model, you can observe a network and try to do inference on the underlying parameters. It's usually difficult in practice because you observe exactly one network in many applications. There's only one World Wide Web, for instance. But this is kind of the way that people have been going. But there are many people from different fields with different methodologies, and it's not clear exactly which ones are better. There's a big push towards information theoretic models where you're looking for minimum description length. There's the classical computer science and graph partitioning approaches like graph cuts and conductance models. And then others that I think are kind of promising based on dynamics, where you look at the different kinds of processes that could take place on the observed network and and try to derive properties such as mixing times on these networks. Because the idea is that, for instance, if there's a densely connected group of nodes in the network, a dynamical process will tend to stay in that group longer because there are not very many bridges out of it. And you can make this precise in various ways. As people have explored this, though, it's become clear that the reality of graphical models and their organizations is not as simple as people had at first hoped, and communities in real networks tend to be overlapping or nested within each other in a hierarchical manner. Real networks are time dependent, so you have to track the time of formation of a community or maybe the time of splitting of one. And so there's been a move towards more complicated and more complicated models that can capture some of the real life properties of these networks. I mentioned that the community structure is useful for what I would call graph coarsening, where you take, for instance, the kind of chaotic structure here, and you basically in your head are going to think of each clump of nodes as a single supernode, and these clumps are kind of connected to each other. So it's a way to reduce a large system to a small system, either intuitively as a data exploration method or rigorously as a way to kind of project to a smaller space. Let's see, is there something I haven't mentioned here?
I have a question.
Please.
Couldn't you give a length to the edges so that there are more stronger or nearer neighbors and so on? That would simplify your computations.
So just in the sense of graph visualization specifically, or just as a general method?
It's a general method.
Absolutely. This is done. It's usually not.
I mean, in internet, you can see the traffic.
Yes.
It's shorter when the traffic is higher, or I mean, everywhere you have.
Right. I mean, they're all one of the
Metric methods.
Right. One of the properties that's really common is that a large number of networks is spatially embedded or approximately spatially embedded, and so that's one way you can do it. The other way that has kind of a metric flavor to it, but is not strictly metric, is the similarity graphs, where, for instance, instead of having a sparsely connected graph, which is what people think of as the normal case, you'll have a completely connected graph where you just specify the weights between all of the nodes, and more similar nodes will have a shorter, or will have a higher weight, which you think of as a shorter distance. So yeah, that's used all the time. I'm going to more or less assume today that the stuff we're working with is not weighted, but the extension to the weighted case is not too hard. Especially in machine learning, the weighted case is interesting because frequently the data comes natively in a form of living in some feature space, and you'll want to map it to a network structure via a similarity map. So that kind of gives you a natural idea of weights. Does that answer your question? Great. The other application that I haven't mentioned that I think is really interesting on the list is information spreading and seeding processes for the purposes of either intentionally spreading or stopping the spread of information and other things. There's a lot of work in disease spread and contagion on this. You know, given a particular kind of network topology, what's the most efficient way to put controls on the network to stop disease from spreading? The defense sector is working hard on this in terms of stopping the spread of radical ideology. So they want to know, you know, where is it going to transfer through? Where should we try and do an interference? And the similar area of study is in echo chambers. There's a lot of work on the different dynamics that can occur on networks that will cause them to kind of separate out, at least in terms of the dynamical processes that will happen on them. So this kind of has a feeling of the phase separation models in material science, where you start with something homogeneous and see if it will continue to be homogeneous or if it will split. In terms of image processing, one application that I really like is image segmentation. This is an example from hyperspectral video. I guess this is a fairly well-known example, but this is a video of of an invisible gas plume with several hundred bands. And the top two pictures are examples of what individual bands might look like in false color. And the bottom is a segmentation of the image that takes into account the information in all of the bands together and across time. You can actually track the objects as they move through time by putting them all in the same graph. And you can see that maroon plume is very clearly detailed. What's impressive to me is that it gets the kind of diffuse edges there very well. The reason there are 4 colors there is not really well understood, but it's probably some kind of staircasing effect. Because under the hood, there's a total variation method going on. Yeah. So once you've settled on a notion of community and decided you're going to look for it, the computation turns out to be really, really difficult. Almost every model you're going to write down is NP-hard. It's kind of par for the course in graph theory. But even considering it's NP-hard, it's in a sense hard even among NP-hard problems because in practical situation the energy landscape is going to be really bad. So there are people. The paper of Good et al. is an example of this that map the energy landscape, and if you're trying to minimize it, looks something like this. And so if whatever energy, it's easy to eliminate some stupid options, but then there are other options that are far apart in the state space that it's hard to distinguish between. And using heuristic arguments, they've found that there are super exponentially many local minima there. So it's really a challenging optimization problem. And one of the limiting factors on the field, I feel, is that even when a model is proposed and used, it's very, very hard to get a guarantee on whether you've solved your model or not in any good sense. And despite what we said about some graphs being spatially embedded, a lot of them are not. So the problem is essentially high dimensional. There is work done on trying to embed the graphs, but it's very far from trivial. And generically speaking, impossible to do. Okay, so anyway, I've talked enough about the state of the art. We can do lots of computations. It's hard to assess if we have the right answer. So there's really interesting optimization challenges in this field. Okay, so let's move into the first example of work that I've been involved in. This is the work that I did with Xicheng Tai, Andrea Bertozzi, and Egil Bai. And there's even a little bit of work before us, a paper by Hu et al. That explored this idea before us, but there's probably the most popular community detection heuristic in use, although it's faced a lot of criticism from people who are pros at community detection, is the modularity criterion, which I'm going to describe now. And it turns out that we can just cast this in terms of total variation minimization. And so I'll describe how that goes. But hopefully we're mostly aware of what an adjacency matrix is. I'm going to use K for the degrees of the nodes. M is the number of edges in the graph. It turns out 2M is usually more relevant as a quantity. G I'm usually going to use to denote a partition, which we can think of as a vector mapping each of the n nodes to n hat communities. Usually in these problems, n hat is one of the parameters to be determined, which is different from the older graph partitioning literature where you could just pick n equals 4 or the number of processors or something like that. And then the quality criterion for modularity is this. Given a partition G and a graph adjacency matrix A, the modularity associated to that partition is this sum, where the sum is supposed to range over all pairs of nodes I and J that are assigned to be in the same cluster by this partition. And the idea behind this is that Aij is considered to be the observed edge value, and the product of k's there is supposed to be the expected edge value when averaged over an ensemble of random graphs. So the idea is if you observe an edge that's stronger than would be expected by random chance, you want an incentive for those two to be in the same community. There are lots of problems with this measure that I won't go into, but the fact remains is that it's the most popular method still in use. So we have to deal with its existence. There are millions of algorithms that I won't go into. I will say, though, that the state of the field is kind of reflected in the fact that the most effective algorithm is basically a greedy algorithm with various bells and whistles on it, which in terms of non-convex optimization is probably not actually as powerful as we could potentially become. The trick is that the other algorithms that are used are typically not good enough for really big graphs. So I'll show you just quickly how you can take the measure that was on the previous slide right here and turn it into a total variation model, a discrete total variation model. So we're going to treat the two sets of nodes separately, or two sets of terms separately for convenience, so the aij terms and the kikj terms. And we're just going to do a simple transformation. So for the first set of terms, the first identity there is just saying the sum of all the in-links is equal to the sum of all the links minus the sum of all the outlinks. So it's just a trivial identity in that sense. And then the second line there is just putting a term to that sum. And the idea behind that term is just that many of you will know what the graph cut is, but I'll define it because there are just some slight variations on the notion out there. If you select a subset of nodes of a graph, the graph cut is going to mean, for this talk, just the count of the number of edges leaving that region. And so you can replace the first set of terms in the modularity with 2m minus a sum of graph cuts over each of the clusters that you've selected. And then for the second set of terms, it's less interesting. You just sum over I first and then j to get a sum of volume squared, where the volume is the sum of the node degrees in each cluster. Which means that the modularity can be written as the sum of graph cuts plus a sum of squared volumes, which is already starting to look total variation-y. The graph cut is one of your best notions of perimeter on a graph. The simple way to see this is if you have a regular grid and you draw a curve through it, a good approximation of the length of the curve is just going to be how many edges are cut by the curve. And the cluster volume also has a similar analogy, and you can prove rigorous results about convergence in special cases. So we're going to define the graph total variation as an analog of the continuum total variation, where you take the integral and of course replace it by a sum, take the gradient and replace it by difference quotients, where the thing you're dividing by is actually 1 over the adjacency matrix value, which kind of gives you the notion of distance like we referred to before. And this, you could give a whole talk on why this is a good notion of graph total variation. It turns out you can derive it or by going through tangent spaces and then gradients and defining an inner product and taking divergences on the graph and so forth. It would take too long to derive it, but you can show pretty well that this is the right notion of total variation. And so the modularity finally can just be written as a sum of total variations plus a sum of volume terms, where the volume terms act as a balancing constraint, a soft balance constraint, because those terms are minimized when the volume of each of the clusters is balanced. Unfortunately, one would like the total variation relaxation to be exact in the sense that the global minimizer is the same as the minimizer when you restrict to the discrete domain, where your functions are indicator functions. Anyway, I'm moving forward. I'll describe how you minimize this model, but first I'll give a quick note on how you manage the non-convexity, because using gradient methods with an energy landscape like this is of course questionable. And so you do actually have to employ some simple tricks that, as far as I know, don't have a lot of theory to them. But they make the solvers work, so we use them. One is recursive splitting. Whenever you split up the network, check out each of the components to see if you can split them further. You have to regularize on n hat to avoid overfitting. It turns out, especially for the second model, if you just put each node in its own class, this gives a perfect fit for the data. But of course, is not very meaningful. Another common move that gets you out of local minima is if you try to merge communities that you've found already to see if that improves your score. And the last point we'll talk about later, because that only applies to the second model that we'll talk about. You can define a mean curvature flow for this model, but I actually didn't implement a solver for that, so I can't say if it's a good idea to do this. But you can do it. Notably, though, the ODE that you get out of this is global in nature because of the last term that has the volumes. So you've got the local term that's trying to adjust for curvature, but you've got a non-local term that's trying to make the volume of each partition equal to each other. So as an ODE, it's actually pretty interesting. The first result that kind of came out of this that I don't think anyone had noticed before is that you just are not going to get a convex relaxation of modularity almost no matter what you do. And the reason for this basically, so U here, because I kind of blew by that earlier, is we can think of it as a matrix where each entry, where the I alpha entry is 1 exactly when node I is in group alpha. This is a pretty common representation of the data. The proof of this is short and basically just follows from the idea that the definition that we showed up there is symmetric under permutations of the group labels. And if you did have a symmetric or a convex relaxation, you could just average over all of the column permutations and use Jensen's inequality to get a better modularity score. But of course, if you averaged over all of the column permutations, that would lead to constant in each row. And therefore, you would have an uninformative answer. And so it turns out that the uninformative answer is always better than the informative answer for any convex relaxation. So if you're going to solve this, you need to do something fancier. The fancier thing that I settled on was the Ginsburg-Landau relaxation, which is a continuum model, but you can, Yves van Gennep and others have proved that you can do this on a graph and still get gamma convergence and properties like that. The idea is, instead of a total variation, you introduce an H1 semi-norm plus a potential well that's designed to make the smooth transition between the piecewise constant bits to be an appropriately small size. You introduce a parameter epsilon that controls the width of the transition region. This is actually much trickier to do on a network because you don't have access to infinitely small length scales. So you get this problem where if you push epsilon too small, the transition region is forced to occur essentially in the middle of the edge between nodes, and there's no chance to transition. But if you make it too big, then the whole solution is blurred across the graph. And it turns out that in a different set of literature, you can show that most real graphs have very small diameter. And so the diffusion happens very quickly. So there's not a lot of room, in a sense, for the transition to take place at all. So there's kind of a narrow range of epsilon that this works well for. And what I think is a really important open problem is to understand how to automatedly select epsilon so you get something non-trivial here, because graphs are small. Yes?
Your T is a double well-like thing.
It's a double well-like thing. It's actually, in this context, a multi-well potential, just because the real constraint on U is that the rows have to have a single non-zero entry.
You might want more than one partition.
Exactly. Yes. But yeah, it's a multi-well potential. that softly enforces the constraints of the problem. Okay. Yep. And so anyway, you can prove gamma convergence for this as epsilon goes to 0. So in particular, if you were to push epsilon to 0, the sequence of your solution would at least have a convergent subsequence that gives you the correct minimizer. Gamma convergence, I feel like gamma convergence is a technical tool that basically describes a precise sense in which these energies will converge to the right energy. And the important aspect of it is that you do get this corollary at the bottom that shows that you're relaxing this in a principled way. When epsilon is small, you're closer to the correct energy, but as epsilon gets bigger, you get a more tractable energy landscape. So there's a trade-off. Okay. So you can take the gradient descent of this Ginzburg-Landau energy, and you end up with an Allen-Kahn kind of equation. The L here is a graph Laplacian, and so just like the spatial Laplacian, it's going to have all kinds of time scales associated to it because it has fast and slow eigenvectors. And so you're going to have to treat that implicitly. I actually found it's nice to treat the other term implicitly too. It makes just details of the algorithm easier. This algorithm, without the volume term, without the KKT term, has been analyzed in one paper by Luo and Bertozzi, where they showed that you get monotonicity in the energy if the time step is small enough. In the continuum case, by the way, they kind of really tout that you get unconditional stability of the algorithm, but I'm not sure if there are additional difficulties in the graph case or what's going on there. One significant challenge in the graph case is that the fast Fourier transform is not available to us, because the standard way to do this in the continuum setting would be to diagonalize the Laplacian and do a pseudospectral scheme. In the graph setting, the hack that everyone has more or less decided on is to approximate the Laplacian by a low rank operator, just find the smallest eigenvalues of it and that correspond to the slowest modes and retain those. Besides being a hack, there is some justification for this via spectral graph theory, where you think that the eigenvalues of the Laplacian do actually encode something about the geometry of space, which coincidentally is what you're kind of looking for here. You're looking for the large-scale geometry of the network. Although in the paper by Luo and Bertozzi, it was showed that the worst-case time step for this kind of algorithm is pretty bad. 1 over the number of nodes is the required time step. So practically impossible. Although in practice this doesn't seem to be an issue. When everyone does these solvers, for some reason all graphs do not have this pathology, and no one knows why. Okay, so if I were to pick an algorithm for doing this, I wouldn't do the Allen-Kahn scheme because of the issues with the range of epsilon being restrictive. Instead, I would use an approximation to called an MBO scheme, which is where you basically do an operator splitting, where you evolve everything but the potential for a little while, and then you evolve the potential. But evolving the potential is essentially just going to be a thresholding operation where each value falls into the nearest potential well. And so that's what you actually do to solve this in practice, is you'll solve the simpler equation, which will not have the same time step restriction, and then iteratively threshold it. You can show in the continuum that this is a good approximation for mean curvature flow. We derive time step bounds so that you don't have to spend all your time tuning time steps. Van Gennep showed that this is indeed minimizing some energy, although it's not exactly the same as the energy that is the modularity energy, and it has the advantage of being really fast, which is helpful because a lot of our data models get really big when you form them into a graph. So I'll highlight, I think I have 3 applications here that just show that this works. The first one is hard primarily because it has a lot of communities in it, and so finding all of them reliably is hard. But because of the recursive partitioning and other tricks, you get 99% accuracy on this benchmark. I showed the gas plumes. Here I'll compare it to some other ways that people might do this. All three of these other ones are also graphical methods. Spectral clustering is kind of the first thing that you would try if you wanted to partition a graph, but it doesn't get the right answer for this problem. And LTV is a method that came out of Stan Osher's group just a couple of years ago, and is tailored for hyperspectral imaging, so I'm really proud that we performed favorably to that one in this case. They do avoid most of the staircasing effect that's present in our method, but they have this funny addition to the plume on the horizon there, which is of course not desirable. What I'm told is in the application that getting the plume is actually the important part of this task. And then Jen Louvain is the more or less greedy solver that's supposed to be the state of the art for the network science stuff. And it does really well, except that it detects a change at the horizon in the plume, which is reasonable, but probably not what we really wanted. And then finally, you can do MNIST with this as an example. You form a similarity graph where each digit is linked with the 10 or so most similar digits to it. And you can get reasonable accuracy with no ground truth. This particular example was an important lesson for us, though, because it's highly sensitive to the initialization. How you initialize the gradient descent matters a lot for this one. And there's a lot of model inadequacy for this problem in the sense that about 25% of the time we would get an objective score that was better than the ground truth partition, but we weren't getting the ground truth partition. And we might not even be that close. We might only be like 90% accurate. So there was some issue with the model not being quite right for this data set, and we're not exactly sure why. It's probably related to how we formed the graph. We might have used the wrong features or something like that. Okay, so the second example of how you can use continuum analogs to get the graph structure is designed for more heterogeneous cases. And it's a stochastic block model based approach. This is much more generic or more general and powerful than the first method, and it's what people who really think a lot about community detection prefer, even though the modularity approach is kind of more popular right now. And we're going to use surface tension to analyze this one, which you'll see has a lot in common with the total variation approach. For stochastic block models, you start with a generative function that proposes how the network that you observed might have come to be. So the idea is in the beginning, there are just n nodes that are identified with their communities. And there's also some affinity parameters, the omega, alpha, betas. And the nodes begin unconnected, and they start forming connections. And each node I looks at all the other nodes j, and with probability based only on the affinity between the classes of those nodes, you make a connection. And so in the simplest case, omega, alpha, beta is just the probability of connection. But there are other models where it's just a parameter in the probability distribution. And there are various elaborations on this, but we'll do the simplest model for pedagogical reasons. And then you just fit an observed network to this model. The simplest way is maximum likelihood estimation, where you just try and learn the parameters omega and the underlying ground truth partition that's most likely to have generated what you observe. So I said that this model is more flexible than modularity. In fact, you can show that modularity is a very special case of this. What this can get that the other one can't is multi-scale structure. So I do an example later on that I refer to informally as the pyramid structure, where you take one community of size 10 and another community of size 20, another of size 40, all the way up till 5,000. And they're not connected to each other, and then you just add very sparse connections between each of the groups. And because of the multi-scale nature of it, it will fool almost all community detection approaches, except for stochastic block model, which is one of the major victories that it achieves is it's not fooled by a single scale. The objective function, when you go through and derive the model and look at the likelihoods, has a log likelihood that looks like this. So you would want to maximize something like this. And you can already tell you're in trouble when you look at this because you're trying to learn the omegas. And there's one that's in a log and there's one that's linear. And so the issue that ends up arising is that they'll try and the two terms will try and counteract each other and push each other to infinity in funny ways. And so you end up with numerical issues that are bad. For instance, omega equals 0 is a common optimal case, but obviously that's going to put the log at infinity. So there's a lot of numerical trickiness because of the multi-scale nature of this problem. But you can do work similar to before and formulate this as a graph cut. I won't go through the derivation. It's a more general version of the first one. And you also get volume terms at the end, which are not strictly volume balancing terms, but their function is to enforce basically it's not a prior, to enforce your expectation of the size of each community, which is essentially what the omegas end up controlling. Because if you've got a group of nodes corresponding to community alpha, and you know that all their affinities with the other communities, you ought to be able to estimate the total number of edges going out of it, because the edges are formed only based on the affinities. And so that's what that second term does. So it is a balancing term in a sense, but it's a much more flexible balancing term. And I changed to these variables big W just because I thought it looked nicer, and for no other reason. And so we hopefully by now you believe that the graph cut. So I should say that cut alpha beta is just counting the number of edges between group alpha and group beta. So it's just a more specialized graph cut. So this is corresponding to geometrically what would be the surface area or perimeter of an interface between two groups or two regions. And then W is going to correspond to what we'll see as a surface tension density. And I'll go into that right now. But there's an analog of this in the crystal growth literature that's been well studied for different applications just in metallurgy. So what you should consider is take a metal, put it at some point in an annealing process, and you'll get what is the crystal growth stage, where a metal, which is composed of all kinds of crystals, denoted at the bottom, the energy of it will essentially be governed by a sum of the type written there, with the omegas being a specific surface energy density that corresponds to each pair of crystals, and then the mu is the measure, or is the size of the interface between them, so the surface area between each group. The reason that there's a specific surface tension energy for each pair of crystals is because the crystal interface is basically caused by a misalignment of the structures of the two crystals with each other. So within each crystal, everything's aligned, but you get an angle of interaction at each interface, and the angle of interaction is different. And somehow through the way that the physics works at the interface, this just makes it so that each interface will have its own energy based on the individual alignments. The actual physics is more complicated than that because you have to, it actually depends on the normal of the interface at each point and things like that. But we're going to neglect that physics for the sake of having a sane model at the moment. But what the dynamics of these models is in order to reduce the energy of the configuration, the crystals will grow into each other, and you'll actually see over time crystals disappear as they're consumed by nearby crystals, and eventually this will arrive at a lower energy configuration where there are fewer crystals, which means the surface area to volume ratio is better and the energy is lower overall. And so a lot of work has gone into understanding this process physically and simulating it accurately because it's tied closely to the material properties of different metals. In terms of what is known about crystal growth models, we know that it follows a gradient, well, we always model it at least as following the gradient descent of this energy in some inner product. Not a lot is known about what the right inner product is. But if you're away from the junction, so you'll see that in practice the crystal network is made up of interfaces and junctions. And so away from the junctions, you get mean curvature flow. And there is an understanding of what happens at triple junctions where three phases meet. At junctions of a higher order, there's not a lot of understanding of what should be done. And because of the model, the lack of a complete model specification for the dynamics, and also just difficulties with the PDEs themselves, we don't have a precise formulation of what this should look like what the descent should look like in the PDE domain. In the case of two communities or two crystals, it's much better understood what happens because you don't have these topological irregularities to manage. There may be someone in the room who knows more about me than this, and if so, correct me. But everything I've read is basically that there's still open questions about this. So while this application is going to be a little bit less rigorous, we can still kind of, at least locally, attempt to do something like mean curvature flow. On a graph, we don't think of mean curvature flow as a continuum evolution because there's not an infinitely small space scale on which that can happen. So you have to specify a discrete time step on which the nodes can change their allegiance. And the way you do that is by a minimizing movements model. This was Yves van Genet's contribution. And you can take the model proposed by Boykov and basically discretize it. And it gives a good analog of curvature flow. The second term there in the mean curvature flow is the distance from the boundary of the original partition. So you minimize the amount of movement away from the original partition while trying to also minimize the surface area. And so actually I did implement this. The simplest way to implement this, and this was actually the most effective of the algorithms for surface tension in my simple tests. And what you do is if you push the time step sufficiently small, the only place where community switching can occur is at the interface, or is at the boundary itself, because in a discrete network you can actually just find the boundary and it's a finite set of nodes. And so you can do this very efficiently by just tracking the boundary nodes and having them switch allegiances appropriately. Yeah, anyway, so that was the most straightforward to implement and the most effective way of optimizing this graph cut model. You can do a Ginsburg-Landau type approach. I have not gotten around to nailing down the details of how the gamma convergence works for that. It's of course more complicated because the matrix W is completely free. And you see the energies interact in more complicated ways here, but you can do the gradient descent here and it works just fine. I will say, so the gradient descent is only going to be done in U. You're only going to try and update the group assignments for the Allen-Kahn part of the equation. If you let W change at the same time, it just becomes wildly complicated. So what you do is you'll evolve the Allen-Kahn scheme until it reaches a fixed point. This is usually really quick. And then you'll update your W, a small amount. You don't let it update all the way until it's local minimum, because then the multi-scale nature of it will make variables fly off to infinity and the numerics go insane. But that's what you do. Well, once your W's are infinite, then you're really in trouble. Anyway, but that's what you do. You have to alternate between an Allen-Kahn evolution and a W update in order to keep things stable. Okay, and you can also do a threshold dynamics. This is actually from what I can sense, the state of the art in the continuum setting is a generalized MBO type scheme. The details of how you do it are really important. I cite a paper by Esadoglu and Otto down there that contains a really good exploration of how this works. But you'll notice the dynamics here are really interesting, because in the two-phase case, the MBO is simple. You'll diffuse and then threshold, and the growth and the phase just kind of evolves by itself. And in the total variation model we talked about before, the modularity model, each of the phases goes through the MBO scheme by itself, in the sense that each class is going to diffuse by itself, and the only time they're coupled is during the thresholding, when you have to push to one of the wells of the potential, basically. But in this case, the right way to do it is to actually couple all of these during the flow itself. And so it turns out that the diffusion of each phase is pushed not only by itself, but by all the phases around it, because of the W term coupling it. And the same with the volume term at the end. And so computationally, this is really truly happening in a n times n hat dimensional space, instead of in an n dimensional space n hat times. And it makes things more complicated. In particular, the pseudospectral scheme you have to work harder to get, because the real operator that you're trying to get the eigenvalues of involves both L and W. But you can do it. You just have to be careful. So numerically, what's really interesting is that this does a really good job of partitioning networks that are actually generated by the stochastic block model. 1.0 means perfect matching with what we would expect the answer to be. And this is with 3 different kinds of stochastic block model networks, including the pyramid one that I described. When you do it on real networks, so these are 3 Facebook networks, you get surprising results, just in the sense that basically, because these networks are not actually generated by the stochastic block model, but only kind of approximately, there's some kind of mysterious noise that affects the 3 algorithms in different ways. And I don't really understand how. But the less than 1 is good in this context. It means that your objective is better than the reference value. So the mean curvature flow deals with the noise very, very effectively, and the other 2 have some issues, and I'm not sure why. I mean, you still get pretty good partitions in many cases, but it's kind of a mystery why the noise affects the different algorithms different ways. So there's a stability question there. In terms of timing, I wouldn't take the exact numbers here too seriously, because this was just a quick MATLAB implementation. If you did a serious C++ implementation, it would be different. But you can see the Princeton network, the Penn State network is an aberration. It's similar in size to the others, but much slower. The Princeton network, for instance, though, has tens or hundreds of thousands of edges, and it just takes a couple seconds to complete in your interpreted language. So it's practical. The Allen-Kahn scheme takes much longer, basically because there's the time step restriction, and enforcing the well potential between each time step is just really expensive. So in terms of efficiency, the MBO is the right way to go. So anyway, so that's the connection that we found. There's basically what people have already been doing and searching for in the community detection literature has really strong analogs with things we've already seen in variational methods for image processing and material science. And it leads to interesting mathematical questions too. You know, the coupled MBO evolution and the nature of the stability under different kinds of noise is really interesting to me. Also, I think there's a lot of progress that could be made in terms of the numerics. I really just did kind of the total variation and mean curvature flow methods that I knew, and they're really kind of the first ones I thought of on the top of my head. But for a very serious energy like this, I think our tools from, for instance, the graph cut methods for image processing, where you actually do get these guarantees on how close to the global optimum you are, have a lot of potential because there's similarity between these methods, these models. Another thing that I think is cool is that the knowledge can flow both ways between these fields. So in this work, I took knowledge from variational methods and pushed it into network science and solved the network science models. But one thing that's worth noting is that the network scientists in the last 5 years or so have put a lot of effort into multimodal analysis, where because in network science, this is just par for the course. For instance, in a food network, there are numerous different kinds of relationships between species. They'll eat each other, they'll be in symbiotic relationships, they'll be in parasitic relationships, and these relationships can evolve over time. The dynamics that occurs on the network of species affects the evolution of the network of species itself. And network scientists have been putting tons and tons of effort into these interactions between different kinds of data describing the same object that's time varying. And so I think there's a lot of potential to pull those tools back in this direction and make progress in multimodal and video imaging where those things happen all the time. You've got different kinds of data about the same object or the data change over time. I also think that there are interesting theoretical questions to ask now that we have discrete analogs of a continuum model. Various versions of consistency could be proven and so forth. Another question that I don't know how to pose properly yet, but it's kind of interesting. There's some literature out there that says that a lot of real graphical models or a lot of real graphs out there are more similar to hyperbolic space than they are to Euclidean space, basically because of the presence of large hubs that a lot of the geodesics go through. And so this is something that I don't really know much about, but surely there is literature out there about how to do evolutions of different PDEs on hyperbolic manifolds, and there could be some potential to solve these models really effectively if we understood how to just port the continuum case over to the discrete case there. So anyway, thank you for listening. We've gotten funding from great sources, and here are 3 references for you guys. The first 2 are papers that I've written. The second one is not quite pushed to the archive yet, but it's in a state that I could give a preprint to someone, a working copy to someone. And then the third one is the only paper before us that used total variation on for the modularity clustering. And yeah, so anyway, thank you for listening. If you have any questions, I'll happy to take them. Yes?
I have 2 questions.
Great.
First one is very naive. You have a sort of density function.
Okay.
Are not where the density function is very high, you could look for the communities. I mean, that would be a very naive approach.
What density function, like a probability density function?
Yeah, you just sit at the node and you go, say, 5 steps, and you call how many nodes are inside this ball, or you make 5 or whatever, and to each node you give this number, and this is a kind of density function.
Yes.
And where it has a hill, it should be a community.
Yeah, I mean, so are you envisioning a kind of Monte Carlo?
I have a second question.
Yeah.
The second question concerns, you mentioned higher order junctions.
Yes.
There is, in the 80s, Kenneth Bracke wrote a thesis with Almgren for varifolds and mean curvature for varifolds, and he could determine constant mean curvature surfaces in R3, like the foam that forms on a beer, and he proved that there are only 3 angles if 3 come together, and 4 can come together and they form a tetrahedron with the same space angles, and nothing else appears. And maybe it's worthwhile to look at his thesis.
Yeah. No, that's interesting. And you said Bracke is the name?
Yes, Bracke. I can look it up and show you.
That would be great. The immediate reaction I have to that is that it's interesting and maybe relevant. The flip side of it is that the crystal growth is a little bit different from the bubble flow because basically because the mass can't be transported quickly to other areas of the crystal like it can in a bubble, and so this means that it does induce some changes in the flow. So the result may be different in the crystal case. But anyway, I would love to see that paper. In terms of your first question, you were kind of envisioning like a Monte Carlo method, basically, or? I mean, there have been lots of people who have basically said, okay, use a gradient approach to get to here, and then do something like a Markov chain Monte Carlo or something to try and estimate marginals or something like that. And those methods are very state-of-the-art. The nice thing about those is that you can do a little bit of theory on them and show that there are transitions between detectability and non-detectability regions and stuff like that. So that is, I think, related to what you're saying, and it's very successful. So you're right.
Oh, okay. To keep
Okay.
on
Right.
time, I'm sure we can talk about this during the coffee break. Thank you.